Who is now with University of Warwick, and he wants to advertise his center, and I forgot the title of your talk. The title of the talk, my darling, is okay. You can read it.
Thank you very much, Sergey. Can everybody hear me? Okay, so it's thank you very much to the organisers. It's a great pleasure to be here. It's very nice to be giving this last talk. I've given the last talk in the conference, in many conferences in the past, and normally there's a bit of pressure on it because you have to finish in time for the conference dinner or for the in time for the coffee break, or some people have got flights to catch or something. But the pressure's really on today, right? And not only that, the tea rooms I can recommend. They're very nice, and so if you want to do that. But, and I've also got a message for Michael, who gave a very nice presentation this morning. He was bemoaning the fact that Holland haven't actually won the World Cup and come very close. Well, England have only won the World Cup once, and if there's anyone German in the audience, they'll probably claim that actually that shouldn't have happened either, because there was an extremely dubious goal that actually happened. So in view of the fact that the World Cup's been going on now for over 70 years and England have won it once, I think it qualifies as a rare event, and therefore I think it is appropriate to have it in the programme. Right, okay. So as Jeff was talking about this morning, this is, I really come from a somewhat different community. I'm really sort of more of a statistician. Most of the problems that I work on, most of them involve applied probability, but they're very much driven by applications in statistics of various forms. So I'm going to give some kind of motivation early on for the sort of things I'm interested in, and then I'm going to eventually talk about this problem called the Bernoulli factory problem, which I think there are some experts in the audience who probably know a lot more about it than I do, but it's something which I found I needed very much for my work, and I'll try and motivate that and talk about the progress that we've managed to make. So this is joint work with three people whose names, if I pronounce them fully, I don't think we'd get to the football in time. Okay, so this is roughly the structure. I want to talk a little bit about what retrospective simulation is, or retrospective sampling. It's an incredibly straightforward idea, has sort of applications all over statistics, all over simulation, which you might find interesting. I'm going to give some motivation of my own personal motivation for the Bernoulli factory problem. I'm going to talk a little bit, very, very brief summary of what's kind of known already. I'm going to present our sort of reverse martingale approach to sampling. And I think in view of this being the last talk, I don't think I'll give any of the sort of formal proofs or anything of these, but they're not really particularly complicated. And I'll say something about the application at the end. Okay, so this is the sort of problems I've been interested in recent years. I'm interested in simulating high-dimensional problems, very often motivated from statistics, and often infinite-dimensional problems. And by that I mean problems where the state space really is infinite-dimensional. For instance, when you have a continuous sample path of a stochastic process, when really to actually identify that evaluation of the stochastic process, you need to actually evaluate it at perhaps a countably dense collection of time points. But what I mean by simulating infinite dimensional is that I want to actually be able to have an algorithm that can pick off finite dimensional chunks of that infinite dimensional problem without having to make some kind of discretized approximation. Okay, and this is something that turns out to be important for certain types of Markov chain Monte Carlo and other types of statistical applications. So that's what I was just saying. So motivation very much comes from statistics problems. I work a lot on inference for stochastic processes, and I also work on problems of analysis of algorithms, Markov chain Monte Carlo algorithms, and sequential Monte Carlo algorithms. One particular application which I'll say something briefly about today is something called the exact simulation of diffusions, which is perhaps the sort of biggest success story of the retrospective sampling idea, where it turns out that you can simulate pretty much all one-dimensional diffusions in a more efficient way than sort of naive discretization methods without having to have any kind of approximation apart from that inherent in any sort of finite computer. And there are other sort of stories in sort of other statistical applications. So, and basically these methods use this incredibly simple idea of retrospective simulation. All that really means, it's a really generic term for saying that we want to take standard algorithms and we want to, in a sort of creative way, change the order in which we do certain types of simulation steps in order to make certain things much easier to compute. So it sounds very, very simple idea, but it turns out there's a lot of flexibility and creativity you can apply to that idea. Okay, so what is it? As just said, so this is essentially just a very simple idea. Typically we work with very simple algorithms, well-known algorithms. Jeff was talking about MCMC this morning. This is the button I should be pressing. MCMC this morning. We won't be doing anything more complicated than rejection sampling this afternoon, and essentially subverting the traditional order of the steps that you might have been taught in your graduate simulation course, perhaps. Okay, I don't want to say too much about, I'm going to give an example in a minute, but it turns out it has very natural allies in simulation, and I just mentioned a few. Catalytic perfect simulation, which is something which some of you may know about. It's related to coupling from the past perfect simulation methods for simulating steady state distributions from Markov chains, and non-centering, which is a methodology which comes straight from statistics for analyzing certain types of hierarchical models. Okay, so the best way to show this is to give an example, and the best example to have is one to come back to the World Cup. So this is an example which, actually, funny enough, when I was a child, I used to think about these kind of problems, certainly not in the way that we have here, but this is a sort of quiz that, you know, the sort of television programs and magazines and things might have, and very simple questions in order to try and get as many as people as possible to actually send their address, so that then you have this database which they can sell on the internet or whatever. So essentially the idea is the question is very simple, and what they used to do when I was young was used to have these television programs in which they'd give a question or perhaps on one particular day, and then a week later, when all the children had answered the question, they all sent in their answers, and most of the answers were actually correct because it's a relatively straightforward question, and then they would just draw one of the winners out at random and give them the prize of a teddy bear or something, right? So this particular, I mean, this is actually quite characteristic of the type of question, and I'm sure you've seen them before. Who's captain? I'm not going to embarrass you by asking you what the answer to the question is, but there's normally one question, one answer which is completely ludicrous. Okay, so even if you don't know anything about football, you might guess that the person with a not particularly English name is probably not the captain of England, unless it's a trick question. And the other two you might not know about, and of course you might just guess at random, and some people, of course, will just know immediately, and of course they will get it right. So you'd certainly expect, but if a large number of people enter this competition, the probability that any individual would actually get it right would be way bigger than a half, right? Certainly it's going to be bigger than a half. So there are two ways of actually doing this, especially we have this live television program the following week in which you're going to announce the winner to the nation. And this is basically what you could do is you could have these n people, you could actually look at each of the n entries and decide whether they're correct or not. The cost of that will of course be order n, and then on the basis of that you've got all the winners and you just pick one at random. Okay, so that's one thing you could do. So this is this is algorithm 1, rejection sampling algorithm. The first thing I do, I basically look at each of the n ones and I actually say whether it's correct or not. Shake the bucket and then pick out a winning postcard. And the cost of this procedure is order n, and of course it's pretty obvious that this is not a very efficient thing to do, especially when most of them are right anyway. And what you should do is you should pick a winner before you even start. So you should basically, what you should do, you should put all the postcards without marking them into a bucket without marking them, and you should then draw a postcard out until a winner is found. Okay, and of course the cost of this procedure is order 1 essentially, or order p to the minus 1. As long as p is not small, that doesn't really matter. Okay, so algorithm 2 is hugely more efficient than algorithm 1, and in terms of as n increases, obviously algorithm 1 gets more expensive. The only reason, of course, why the BBC didn't use algorithm 2 was they didn't want to have some kind of way of embarrassing sort of young children in one of these programs by announcing that someone was the winner and then saying, oh, I'm sorry, that person got the answer wrong. and having to actually go on to the next person. So this was not something you could actually do on live television. So they used to do algorithm 1 that was highly inefficient. Of course, it would be very nice if they could do a kind of rejection sampling live on television and somehow cut that, but I don't think that's something that the BBC producers had thought of at the time. But you see, I mean, the sort of straightforward, all we've really done is change the order of these two operations with a huge computational gain. And most of the time I'm interested in problems in which the computational gain is not in terms of the size of a problem, because the size of the problem might be infinite, but it's basically finding an infinite computation problem which you can do in finite time. Okay, so let's go back to rejection sampling. You all know what rejection sampling is, I'm sure, but let's just sort of describe it. F is a density of interest, so we're interested in simulating from F, but we can't. G is another density, we can simulate from G, and F over G is bounded by some constant capital K. So rejection sampling would work by simulating from the density we can simulate from, and then computing this ratio, Fx over K, G of x, simulating a uniform random variable to actually activate the accept-reject decision. Okay, so I've labored the point that of essentially what the steps are. You all know what the steps are. However, the point is that really all you need to do is to carry out this accept-reject mechanism. The accept-reject mechanism doesn't necessarily really need to know what P of x is explicitly. Neither does it necessarily need to actually compute all of x. If x is an infinite dimensional object, or if x is a very high dimensional object, you might like to get away with simulating less from x if actually the decision that you would make in terms of accept reject would actually not depend on that. So what we do in rejection sampling, in retrospective rejection sampling, is we try and give ourselves a framework in which we can actually do the accept reject mechanism essentially with minimal information from x. So this is a description of a retrospective rejection sampling. There's some slightly different formulations you could adopt, but this is a simple thing that you can do. So the first retrospective thing is that we start with a random seed. In this case, this uniform random variable is what we call an auxiliary variable. And I'm going to, in abstract form, I'm going to find some function which is a function of our auxiliary variable that was easy to simulate, and x. Okay, and a set A which might depend, well, typically would depend on v, such that in some sense if you integrate out v, if you take an expectation over this v, then actually the probability is correct. So none of this involves us, at least in theory, we haven't insisted that you need to be able to compute anything like P of x. And moreover, this object HV of x needn't necessarily live on a state space that's anything like as complicated as the state space of x. So typically in the examples we look at, if x is an entire stochastic process, for instance, then HV of x could perhaps be some kind of random discretized skeleton of that sample path. Okay, but a finite subset of information contained in the whole sample path. Okay, so what we would do here is then we would simulate, instead of this, once we've got this v, instead of simulating x, we'd simulate hx of v and accept in this way. So this is doing exactly the same. It's very easy to see that this is essentially carrying out exactly the same thing. I'm using the randomness in v as part of the rejection sampling, but there's nothing to stop me from doing that. Another restriction, which turns out to be an interesting one to solve in different contexts, is that there's no use doing this if once I've done this, the accept reject mechanism on the basis of HV of x is so complicated that actually I can't then access further bits of x which I'm interested in. So this fifth step is something that we need to be able to do for it to be useful. We need to be able to fill in the missing bits of x from the simulation, and this is essentially just a conditional simulation. So it's a conditional simulation of x conditional on this. Okay. So these are the sort of driving forces behind retrospective rejection sampling. Yes, okay.
To some extent, after step 4, you found maybe you simulate some function of x, not itself, yeah?
Yes, yes.
Like projection, whatever.
Yes, so exactly. So typically it will be a projection, but because you've got this extra randomness in v, the actual projection that you take is random. So you could be taking any. So when you marginalize over all possible projections, if you like, you're getting the right probability. Okay, so that's so you're using randomness in a very powerful way here to say I only need to look at certain parts of the of X. Okay, I'm going to give one simple example of this. Which turns out to be quite useful for various applications in statistics. This is quite a common situation where we have a sequence of numbers, P1, P2, P3, etc., with these properties. You can bound these numbers above by some other numbers, Q, in such a way that I understand the tail probabilities of Q. Okay, so it turns out this is a very natural assumption for statistics because these Qs can typically be constructed via prior distributions in the situation where the P's are posterior distributions. Okay, but what I don't know here is that the sum of the PIs, I don't know what the values of the sum of the PIs are. So I know this probability distribution only up to a normalization constant. Again, that's a classic situation in statistics, in Bayesian statistics, where you don't typically know normalization constants. So what we would do if we knew what what I'm saying here, because in this context here, the P's are probabilities. So if the P's really were probabilities, then I could use the inverse CDF method, which, as we all know, just as the following, it calculates the normalization constant. Oh yeah, so the P's are unnormalized. So I would calculate this infinite sum, and then I'd simulate a uniform random variable, and essentially just set X to be the smallest J value, such that the normalized probabilities, the real probabilities I should say, are bigger than or equal to U. So this is how rejection sampling would work. But the problem here is the infinite computation step is step 1 here, where we need to compute this infinite sum. Okay, so how can we avoid that using retrospective methods? Well, okay, there's a lot of notation here, but it's not really doing anything too complicated. All we do is we look at some bounds, and the bounds are obvious, right? In some sense, that a lower bound is the sum up to J of the probabilities. A lower bound for the infinite sum is the sum up to J. Completely obvious. An upper bound can be just produced by the same thing, except adding on that upper bound for the tail that we know about. Okay, so these are things we can have. And of course, we have very, very nice nesting properties here. As J increases, these bounds get better and better and better. Okay, and what we can therefore also define is we can we can have upper bounds for the probabilities, for the cumulative probabilities, the CDF, by looking at the sums of the probabilities divided by the lower bound, and conversely we can get a lower bound for the cumulative probabilities just by looking at the sum of the probabilities divided by the upper bound for the sum. Okay, so and then essentially what we do is we just have the following algorithm. It's a retrospective algorithm because the first thing we do is we simulate the uniform random variable. Okay, so we don't need to, we basically have that first of all. And then all we do essentially is we increase J until our lower and upper estimates for what the outcome of this algorithm actually give you the same quantity. Because the infinite version then will give you something in between, and if they have the same value, this must be the same thing. So this is a method in which you can essentially do all the calculation without infinite computation, just by looking at these a large enough J. And of course, the running time of this algorithm is random, but it's very easy. It's very straightforward to actually calculate the characteristics in terms of the computation time, the tail probabilities, etc., of this retrospective algorithm. It turns out to be very efficient in many situations. Okay. Right. Okay. So this is a sort of general description of what the Bernoulli factory problem is, and this situation is intriguing problem that you have a probability P, which is unknown. Okay, but I have a black box, an algorithm of some kind, which can actually simulate events of probability P. They can simulate such events, but I don't know what P is. Now that may not seem very natural to you, but it turns out that there are many situations in statistics where we can actually do this, and it's important. And very often in rejection sampling, using infinite dimensional objects like diffusions, we're in a situation where we can do the simulation, but we really can't calculate the probability that we're doing it for. Okay. So the question is, what can we do with this? So, suppose we have this black box that does P coins. What if we have some function which might have some fairly nice properties? Can we construct a black box that simulates f of P coins?
How can you simulate P coins if P is less than 1?
Sorry?
P is integer or not?
No, P is just a number between 0 and 1. So P is just in 0 and 1. So a P coin is a coin which takes the value 1 with probability P. Okay. So it turns out for Markov chain Monte Carlo in particular, a crucial function you might look at is f of P is the minimum of 1 and 2P. As Jeff was talking about this morning, very often in Metropolis Hastings algorithms you have acceptance probabilities which look like the minimum of 1 and some kind of ratio. Here, actually, it's so it turns out that if a number here is, if we have a multiple of P which is less than P, then it's trivial. If that number is bigger than P, it turns out to be very hard. Okay, so this is just an example of the Bernoulli factory problem. Just some brief history. So there's a nice paper in 1992 by Perez, where you can find most of this information. As with many of our modern algorithms, a lot of this really came down to von Neumann did the first sort of real thinking about this problem, and he thought about the problem of how you might make coins fair, which is a reasonable thing to want to do. Of course, it's a simple problem. You want f of P to just be the constant function a half, and there's a very nice simple algorithm for this, which is essentially tries to sort of counterbalance P and 1 minus P in a nice symmetric way. And you could probably come up with this yourself if you were given 5 minutes to think about it, but I won't give you 5 minutes. So essentially what you do is you basically take two consecutive observations, xn and xn plus 1, and if this takes the value 0, 1, and if it takes the value 1, 0, you stop, and obviously those events have the same probabilities. And if you don't stop, then you continue and you do the same thing again. And it's easy to see that by symmetry the probability is going to be a half. Okay, so we can do simple things by that, like that, and there are certain functions, other functions for which it's straightforward, but that's certainly nothing like a general picture. Then there was so von Neumann did fp equals a half. Soren talked about fp equals 2p, but this turns out to be a very difficult problem and with a very interesting history. This is essentially the problem. I want to just basically talk about the problem of ours, which originally motivated our interest in the P2P problem. And this is basically to do with the simulation of diffusions. It turns out to be not the exact algorithm that you will have heard me talk about if you've ever heard me talk about exact simulation of diffusions. This is actually an algorithm that predates this. This is actually not as efficient and actually has stronger conditions attached to it than the sort of current methods that we're looking at. But it's closer in spirit to the Bernoulli factory problem, which is why I'm presenting it here. So the problem is basically I want to simulate from a diffusion. I want to simulate suppose I just want to simulate from the value of a diffusion xt at time capital T. Okay, what is this diffusion? I'll make it simple as possible. It's one-dimensional. It has a diffusion coefficient 1, and it has a drift given by alpha, which is a known analytic function, which will have some regularity conditions, which I'll present shortly. Okay, so a little bit of notation, which you don't really need to know too much about, but just to say that Wx is just Brownian motion started at x, and Wxu is Brownian motion, is a Brownian bridge. In other words, Brownian motion started at x, but conditioned to finish at u at time t. And we need the following conditions on alpha for this particular version of the exact algorithm to work. We want the drift function to be sufficiently smooth differentiable. We want this function here, which is a little bit like, if you ignore the e to the capital A term, is a little bit just like what Brownian motion would be at time capital T without anything else. So in some sense, this capital A here is perturbing the distribution of Brownian motion at time 1. Okay. What is capital A? Capital A is just a term which is the integral of the drift. So it's not something that necessarily we would calculate normally if we were simulating diffusions, but it turns out to be a sort of very important thing for this method, and actually turns out to be quite interesting in general approximations for diffusion sample paths. Okay, and this is the condition which is the strongest condition, really, and this is the one which largely you can actually get rid of this condition completely, essentially. But the function alpha squared plus alpha prime, its derivative, is actually bounded, well, that divided by 2 is bounded below by curly L and above by some value which I'll just call curly L plus R, which will stand for a range. Okay? And then once I have this, I'm going to define a function phi which renormalizes this function alpha squared plus alpha prime over 2 so that it lies in the box 0t cross 0, 1. Okay, so phi 0 is definitely going to live in 0, 1, no matter what the sample path of a diffusion is. Okay. A little bit more notation, I'm afraid, but so let Q be the probability induced by the solution of that stochastic differential equation. So Q is the thing we're interested in. Let W just be Brownian motion. Okay, that's the thing that that's something that we know we can simulate from. And then we've got something which is a kind of a halfway house in between the two, which I call Z. And Z is something which looks a bit like Brownian motion, but has a Radon-Nikodym derivative with respect to Brownian motion, which is proportional to e to the minus a bt. Well, 1 over its, so it's 1 over its Radon-Nikodym derivative is e to the minus a bt. Okay, so what's that doing? Well, I certainly don't want to go through the details of this, but because the Radon-Nikodym derivative is only a function of capital T, this tells you that Z essentially has similar dynamics to Brownian motion, except all we've done is we perturbed the distribution at time 1. Okay, but conditional on everything at time 1, the dynamics are identical, so the conditional probabilities are according to a Brownian bridge, etc., etc. Okay, and the whole point is that I'm going to be using Z for rejection sampling here. Z is something I can simulate from by various ways, and if I write the dq by dz for distribution of interest by dz, which is the thing I can simulate from, this is the rejection sampling. It turns out to look like this. Okay, it's an expression for this which you can just get via certain calculations from the Cameron-Martin-Gersanov formula. Now I'm going to so this is quite a nice quantity. It's actually just a Riemann integral of along the sample path, and it's a quantity which I know is nice because phi here essentially lies between 0 and 1. So I've got a lot of control over what's actually happening in there. And in particular, I know it's less than or equal to 1, so I know I can do rejection sampling, at least in theory. Okay, so if I want to do the exact algorithm using the Bernoulli factory problem, therefore, what I'd like to do is be able to simulate from an event of that probability, that Radon-Nikodym derivative. So I could simulate a random variable u according to this distribution h, which is just the distribution of the proposal distribution for rejection sampling at the terminal point t. And now what I'm going to do now is I'm going to do this, I'm going to generate a CS coin, a coin which has a probability S, where S is e to the minus RTJ, where J is this quantity here. Okay, and once I've done that, if I accept, then I output everything and then I stop. If CS is equal to 0, then I go to 1. So this is, I'm not going to talk about the details of how you implement this or anything, but this is a rejection sampler. It's mathematically valid. It turns out you can actually implement this very straightforwardly. It's about sort of 4 lines in R or something. It's very straightforward. The trouble is I want to simulate a CS coin which has a probability e to the minus RTJ. Okay. For simplicity, I'm going to assume RT is less than 1. Again, that's something you can get rid of. I'm going to assume that. But the point is that actually it turns out that J is a much nicer quantity than e to the minus RTJ. And we can simulate from events of probability J. Okay, J is just a probability. I can simulate from events of probability J in a simple way, which I'll just show you in a minute. And so the Bernoulli factory problem here will be in order to be able to see if we can simulate from the CS coins, which have a probability e to the minus RTJ. Okay, and how can we do this? Just to say how we simulate, how we do that, simulate those J coins. Well, we do it in the following way, and the retrospective sampling idea says, first of all, I simulate 2 random variables, one which is uniform on 0t, one which is uniform on 0, 1. And I just let Cj to be the indicator function that this random draw here is less than or equal to phi evaluated at the sample path evaluated at chi, which is the other random. So all I have to do here is look at my sample path at one particular time, this chi object here, and then evaluate this indicator function. So I don't need to look at the whole sample path in order to actually make the accept-reject decision. And then keeping in mind what we were talking about earlier about rejection sampling and retrospective rejection sampling, we need to then be able to reveal further parts of the sample path if we then want to. But we recall that all of the dynamics of this stochastic process conditioned on its endpoint are just those of a Brownian bridge. We can then go back and fill in bits if we so want to. So this decides that we've done the acceptance, and then we can basically fill in the rest of it if we want, because that's all Brownian bridge stuff which is not affected by the accept-reject decision. Okay. But then this leaves a problem of how do you actually solve the Bernoulli factory problem here? How do you go from the Cj coins to the e to the minus RTJ coins? Okay, so that's the problem. Just a little bit more about the background. So the Keenan-O'Brien result, this is a sort of classic result in the area which I think did push the area on hugely. It's quite an old result now, but it's not a constructive one. Essentially showed that a necessary and sufficient condition for you to be able to solve this is the following. And essentially the important criteria is that basically f is continuous, and for some natural number n, you have this lower bound on the minimum of fp and 1 minus fp. Okay, and this does rule out some sort of interesting things that we've already talked about. In particular, the minimum of 1 and 2p, which is a bit of a blow because that's important for MCMC, but it doesn't rule out the minimum of 1 minus 2 epsilon and 2p, which fortunately is something we can use in MCMC instead by a minor modification, making the algorithm slightly less efficient, but it's something we can always do. Okay, but the proof is not constructive, and it doesn't necessarily help us if we actually want to really apply this result. Time's going on a little bit, so I'm going to speed up a little bit, but just to say that the other, I think, sort of very important advance, which was very important for our work and stimulated what we did, was the Naku-Perez paper in 2005. It's very intuitive as well. Essentially what they were doing, the Naku-Perez paper, was to use polynomial approximations to this function f of p. And the polynomial approximations were a lower bound gn and an upper bound h of n, which have the properties that they're polynomials which are converging upwards from below and downwards from above. And so these are the conditions we wanted. Well, we wanted a term by term bounding between these a's and these b's. In the first version, actually, this can be relaxed, but the first version of their result, these quantities have to be integers. and the lower bound and the upper bound both have to converge. And also this is a condition, essentially this inequality here is an inequality basically as polynomials, looking at every single term in the polynomial being ordered in this way. So quite strong conditions, but conditions that turns out to be quite natural for some interesting problems, including some of the ones we've looked at already, like the minimum of 1 minus epsilon and 2p. But, so this is a very nice paper. The trouble is that actually to implement the, and in some sense the proof in this paper is constructive, but it's not constructive in a mathematically, in a practically useful way. And it turns out that you have to do some really sort of extraordinary computations to get this thing to work in practice. And I'm not going to go through this in any detail, but it turns out you have to look at numbers like 2 to the 2 to the 25 in the kind of problem that we were looking at. So it turns out that there's not a natural way of actually applying this. In some sense, what you have to do is you need to look at very big sets, and you have to explicitly store explicit orderings of very big sets of long strings of zeros and ones. Anyway, so what we wanted to do was we wanted to find a way of implementing something like the Naku-Perez approach in a way that used retrospective sampling. And so this is what we did. We sort of thought, well, maybe we can attack this approach almost from first principles. Okay, so we're going to have a series of algorithms. Algorithm 4 is going to be the one that we can apply to the Naku-Perez kind of construction. And but it is sort of, I think, having the sequence of them actually really to sort of demonstrate the sort of it's also how we actually develop things in terms of ideas, but also I think it helps understanding doing it in this way. So first of all, this is trivial, really. Suppose I want to simulate from an event of probability S. This is equivalent to finding an unbiased estimator of S, which only takes values in 0, 1. Okay, okay, so that's, well, proof of that is straightforward. You could give it to your graduate students and they could do, right? So this is essentially what we do, but just to say what we're really doing here is we sort of do a retrospective sampling in the sense that we draw a uniform random variable G0 and we compare it to S. And then you work out the probability and hey presto, it's the right answer. Okay, so that's well known, and it's a nice thing to do. So we can certainly, so the only difference between this and what you might do in a sort of trivial inverse CDF thing is that what you're doing here is you're using a random variable, and the unbiasedness is something that's not a problem. So the fact that you've got a random estimator is fine as long as your random estimator takes values in 0, 1. Okay, and that's your algorithm. Okay, here's another method which is very close to the algorithm I was talking about at the beginning. Here you have a situation where you have now a deterministic sequence of lower bounds and upper bounds. Okay, the lower bounds increase up to S and the upper bounds decrease down to S. Okay, well, the algorithm, which we don't really need to sort of prove anything about, but essentially we do the same thing. It's retrospective because the first step says simulate the random seed, the G0, and then we essentially compute the ln and the un, and we iterate this until we've got an ln and a un which agree on the outcome. In other words, they both say yes, it should be a 0 or it should both be a 1. While they disagree, and one of them, when G0 actually is nested in between the two, then you continue. But you only continue as long as you need to. Just a brief note, the tail probability of this algorithm is explicitly easy to write down in terms of difference between un and ln. So that's something which we can understand very well. So for instance, if a un and ln converge exponentially, which they may well do, for instance in the context of the Bernstein polynomial approximations, then you can control this tail very nicely and there aren't problems. Okay. And I have to say this is a very old idea. It's a very neat idea due to de Vroij. So can we somehow combine the monotonicity and the stochasticity? Well, okay. Well, the first thing to do is yes, you can, and everything's fine. So here we have monotone stochastic bounds. So now the only thing that's changed here is that everything's, these things are random variables, but they still maintain almost sure ordering. So the lower bounds are increasing, and the upper bounds are decreasing, but the expectation properties are the same. Okay, and I'm just writing down for notation's sake here some of the sets of information. So Fn is information contained in both the lower bound and the upper bound at time n, and Fkn just essentially takes all the information between k and n. Okay, and again, I'm not going to. The algorithm does what you think it would do, and it just combines the first two that we actually have. Okay. Right. Okay. So I've actually given the proof there, but so I'm not going to go through this. It turns out that algorithm 3 works, and it's kind of neat. But the only problem with algorithm 3 is it needs this almost sure ordering on the upper bounds and the lower bounds. So the upper bound has to be increasing, the lower bound has to be decreasing. So we'd like to be able to relax that, and what's the natural way to relax that is to have something like a martingale condition or a super martingale and a sub martingale condition, in which essentially it might be much easier to get in the context of any particular application. And we thought about this for some time, and it turns out that forward super martingales and sub martingales are not the right thing, and you can't get these things to actually do what we want. We played around with this for quite some time, but there's a trick which allows you to actually work, to make this thing work, and it's essentially a reverse time martingale technique. Basically the idea is we have the following setup, which I'll describe in a second, but the purpose here will be then to apply this reverse time martingale technique in order to convert these reverse time martingales into a derivative process which actually satisfies the conditions for algorithm 3. So that's essentially the strategy here. This is just something which we're going to try and, these are conditions which are weaker, and then from this we can actually derive some other, almost sure increasing and decreasing sequences which then can satisfy algorithm 3. Okay, so what are these conditions? So these conditions now are ln less than un, so again we have a bound on the lower bound is less than the upper bound. These aren't bounds, of course, because they're random, so but in expectation they're bounds. They all take the values in 0, 1, that's important. The L's are increasing and the U's are decreasing. The expected value of the L's is increasing up to S, and the expected value of the U's is decreasing down to S. Okay, they're the conditions so far, and we want to weaken the third condition. And it turns out that the condition we need is the following. So if I look at the expected value of Ln minus 1, conditioned on all the information from n to infinity. Now, by the Markov property, which in all practical applications these things will be Markov, this is just the information contained in n, and we want this to be less than or equal to n. And then we have a corresponding condition on u, so we have a sub-martingale condition and a super-martingale condition. Okay, and it turns out this condition is relatively easy to check if you have a sequence of p coins, as it will turn out to be in the Bernoulli factory problem. These things are easy to calculate because these are just a sequence of IID observations.
In the top conditions, can you just say that ln's are converting to a random variable which has mean s?
Yes, that's correct. Yes, yeah. Okay, so how does this algorithm work? It's retrospective, so the first thing starts with a random seed, which was actually going to do the decision for us, the G0. It's now, what it's going to do is it's going to, instead of look at these U0s and these L0s, it's going to derive something, it's going to sort of talk about something called L0 tilde and U0 tilde, which I'm going to derive from the U's. And how am I going to do that? Well, I'm going to basically, first of all, it's going to sequentially work up, so I'm going to obtain Ln and Un in some kind of Markov updating fashion. And once I've done that, I'm actually going to just use them in order to calculate something slightly different. Okay, so what am I going to do? I'm going to calculate ln star, which is the expected value, expected value of ln minus 1 given fn. Okay. And I'm going to calculate un star, which is this expectation here. And then I'm going to compute something which looks a bit strange when you first look at it. I'm going to iterate these ln stars, ln tildes. So the ln tilde is ln minus 1 tilde plus some kind of correction. But I've constructed it because of the sub-martingale condition, the sub-martingale condition for L, to be almost surely increasing, because I'm going to be looking at ln minus ln star, which because of that condition is bigger than or equal to 0. And I do a similar thing for the U-bound, and the algorithm then essentially works on the basis of these ln stars. So what this algorithm is doing is it's trying to construct these ln stars, these ln tildes, and un tildes are essentially things that we can throw directly into algorithm 3. And all we need to do, therefore, is to check that those conditions hold. And so this is how the algorithm finishes, in the same way as algorithm 3 would. And again, I'm not going to go through the proof, but the key feature is because of the way we've constructed things, all the conditions of algorithm 3 hold. In particular, the monotonicity properties, the bounding properties, the fact that the lower bound's always less than the upper bound, and actually we have a mean preserving property in the sense that the expected value of ln tilde is equal to ln and un. Okay, and that checking those conditions is not that difficult. It's straightforward calculations really once you've kind of got the idea, and that's what it is. Okay. Time's going on. How long have I got to go? 5 minutes, okay. It turns out that we wanted to use exactly the Naku-Perez algorithm, but we had to do a minor modification of what was in their work. Instead of the last condition, it turns out that we need a condition on the coefficients, which is this condition here, which is a condition that relates the coefficients at n to the coefficients at smaller values of n. And it turns out that these conditions here are exactly the reverse time submartingale and supermartingale conditions that we need. But these are things which come naturally from the Bernstein polynomial approximations that were presented in the Naku-Perez approach. Okay, I don't think I've got time to go through this, but it turns out that we can apply, well, I'll just write down the algorithm here. The key feature here of the algorithm is that all I need to do is that to define these ln un random variables as follows. If the current, after n trials, if the current number of successes is k, then I'll just let the ln, the lower bound, just be this A object, and un is just the B object. Now these aren't going to have the monotone properties that we'd like for algorithm 3, but we can then derive from these the ln tilde and the un tilde variables, which we can use for algorithm 3. So in other words, we can actually apply the reverse time martingale to those. And I'm not going to go through the rest of the proof, but essentially that all works. Okay. I was going to go briefly through how you might do other functions. So I wanted to go through the diffusion process example from the beginning. How might you go from events of probability p to events of probability e to the minus a constant p times p? And it turns out there's a neat algorithm for that which doesn't actually need the reverse time martingale approach. It turns out you can do that in a fairly direct way. And that's related to some other work we've been doing. And it turns out when you unravel that in the diffusion context, it turns out that you have to actually construct random skeletons of diffusion sample paths in order to actually carry out the rejection sampling algorithm. Okay. So with time moving on, and I know no one wants to miss the tea rooms or the football. So what have we done? So this is I think this is a practically implementable solution to the Bernoulli factory problem. It's not necessarily, I would say, a robust method. Our methods blow up in terms of computation time when f gets close to 1 or corresponding to f gets close to 0 or something. But it does turn out that actually that we can do, for problems where the f of p doesn't go too close to 1, we can actually apply these things routinely and get sort of thousands of observations per second and things like this. But it's still, I say, we haven't completely solved the problem in terms of being able to just solve any black box solution of this type. We're using this a lot in inference for diffusions and for simulation problems for diffusions, and that's kind of ongoing work. And just to sort of say that actually the retrospective simulation ideas I think are very straightforward, but surprisingly powerful in lots of different situations, massively reducing computational costs. We were very surprised about both how simple they were and really how many applications we could find in which they made a real difference. So thank you very much.
Well, you make the claim that one can do exact simulation of almost any one-dimensional diffusion. Yeah. As you wrote it, you had a diffusion coefficient that was equal to 1. So what is some non-constant function?
So that's a good question. So if you have unit diffusion coefficient, then all you really need is some smoothness in. So you need something like the derivative to exist and be bounded. You don't even need it to be continuous. Plus, you need it to be a non-explosive one-dimensional diffusion. But apart from that, there's nothing. If you have a diffusion coefficient, then you need to have some smoothness in the diffusion coefficient, and you need to essentially what you do is you transform the diffusion coefficient to unit diffusion coefficient via the usual Lamperti transform, and by doing that, you then basically any problems in the diffusion coefficient get translated to conditions that you actually have to have in the drift. Okay, so the usual things like having to make sure that the diffusion coefficient stays away from 0 is something that you need to have, and you need to have kind of smoothness. Now, when you get to multivariate diffusions, that's a much more complicated situation. Now, so very often you cannot transform to unit diffusion coefficient, and you can only apply the methods then when you can find some kind of diffusion with the same diffusion coefficient structure which you can simulate, and that's very rare. Okay, so but it's in a general case. In the very general case, you can't do that. But in many cases where you still have fairly straightforward diffusion coefficient structures, you can do exactly the same in many high-dimensional problems as you can in small-dimensional problems.
So in computer science literature, you have these lower bounds on algorithms. In this setting, do you see, can one develop lower bounds, for example, for generating a sample with probability 2p? You'll need at least that much computational effort. Can one do something like this?
Well, yeah. I mean, it very much depends on the particular application. I mean, in the 1 min 2p problem, I mean, it really depends on the bounding function. To be honest, the only thing that really holds it back is how good the approximations are. And in the context of the Bernstein polynomials, the problem is essentially that you need as I said in algorithm 1, you need to make sure that whatever you're using as your estimators, they have to be in the interval 0, 1. So your upper bounding polynomial has to be actually less than 1. So basically, it turns out that once that's less than 1, then the computation is minimal. So the simple answer is yes, but I mean it all depends on how good your bounding. If you've got a superb way of bounding your function f of p.
No, my question is, can we say that no matter what algorithm you have, it'll require at least this much effort?
Well, a lower bound.
In that sense.
I'm.
Is there literature on that?
No, there's certainly no literature on that. I mean, but if you, I think that in some sense, that's not going to. I'm not sure how easy it is to define the question correctly, because in some sense, if these bounds get better and better, the better and better these bounds are, then the computing time goes to 1. So you need to somehow. I mean, of course, that's not realistic, but then you need to sort of define what you mean by closeness and what's reasonable to be close, in some sense.
More questions? So thanks, Gareth.